What is going on, guys? Welcome back. In this video today, we're going to train a convolutional neural network built in PyTorch to classify images of brain tumors, or at least scans of brains, and then to classify if there is a tumor, and if yes, what kind of tumor it is. So this is a perfect machine learning project for beginners or intermediate programmers. Let us get right into it. Alright, so our goal for this video today is to build and train a convolutional neural network from scratch in PyTorch, which classifies different types of brain tumors based on MRI scans. And for this, we're going to use a Kaggle dataset called Brain Tumor MRI Dataset. It's quite straightforward how it's structured. We have a testing directory and a training directory. Both of them have the same 4 subdirectories. One of them is called no tumor, so that's basically the negative example of a healthy brain. I mean, positive in terms of it's a good thing, but negative in terms of it's not a positive classification, it's not a tumor. And then we have the 3 different types: glioma, meningioma, and pituitary, or I don't know how these are pronounced, not a medical expert. But we have 3 different types, and basically these directories are just images of scans. So these are the healthy brains. Then here we have one type of tumor. Then here we have another one, and so on and so forth. I think it goes without saying, but of course, none of this is medical advice. Don't treat this in any way, shape, or form as something that you should be using to diagnose yourself or others. This is just a programming exercise, a machine learning exercise, just a disclaimer here. But what we're going to do is we're going to download this data set and we're going to train a convolutional neural network in PyTorch on it. And for this, you want to go to the download button. You will find a link to this data set in the description down below. Just download the data set as a zip file, and then we're going to move on. We're going to go to our tutorial directory, or whatever directory you use for your work. And in here, I already have the archive.zip. So this is the data set. I can briefly unzip it so I can extract all the images. And then what I'm going to do is I'm going to create a directory data, and then I'm going to just move training to data and testing to data. And that is going to be just our data directory. So let me remove the archive now. And now in my case, I'm going to set up my project using UV. So my package manager is UV, which means I'm going to do UV add to install packages. However, if you don't want to use UV, you can just go and use pip. So pip or pip3 install. And the packages we're going to need today are PyTorch, so Torch Vision to load image data sets easily, and Matplotlib for a simple visualization in the end. In addition to that, I would also recommend installing JupyterLab, which is the development environment that I'm going to use today. If you don't want to use that, you can use ordinary Python notebooks, so ordinary Jupyter notebooks. But I would not recommend working in a single file and running it, because you want to execute individual cells. Maybe you want to do some exploration, some testing, and it doesn't make sense to have everything executed at once. So I would recommend working with IPython notebooks, in my case, JupyterLab. So as I said, I'm going to use UV. So I'm going to say UV init to create a project here, UV add to install Torch, Torch Vision, Matplotlib, and JupyterLab, like this. And now what I'm going to do is I'm going to say UV pin Python, sorry, it's UV Python pin 3.11 to pin the version. And then I'm going to say UV run JupyterLab, like this, with a space in between. Hopefully this works in terms of using the correct instance. I can now create a new Python notebook. Let's save that as main IPYNB, and let's see if I can import Torch. There you go, I can. I don't get the error message, so I'm using the correct instance here. Now we're going to delete the main PY file. We don't need that. The rest here is just UV stuff. If you use pip, you don't have that, obviously. And what we're going to do now, what we're going to start with, is we're going to start with the imports. And the imports are the following: import Torch, as we already said. Then we're going to say from Torch import NN and Optim for the different layers and for the optimizer. Then we're going to say from Torch Vision import datasets and transforms. And then from torch.utils.data, we want to import the data loader. These are the imports. We're going to import Matplotlib later on in the end to visualize some images. But that is now the basis, and then we want to determine what kind of device we're going to use. We want to use a GPU if a CUDA GPU is available, otherwise we're going to fall back to the CPU. So I'm going to say here device is equal to, and then we're going to say torch.device CUDA if torch.CUDA.is underscore available, else fall back to CPU. So we're going to use the GPU if it's capable of being used, and otherwise we're going to fall back to the CPU, which is much slower. Now, next up, we want to define transformations. So when we take the images, we want to do certain transformations before we use them. One of them is we want to resize them to a certain size, to 128 times 128 pixels. We want to turn them into a tensor, and then we also want to normalize them so that the neural network doesn't have to work with the raw pixel values. We want to have the data normalized. So we're going to do the following. I'm going to create here a list of transformations called TF, and we're going to say here transforms dot resize is the first one. We pass here a tuple of the shape 128 times 128. Then we're going to say the next transformation in the pipeline is the to tensor transformation, so turning it into a tensor, and then transforms dot normalize, and here now we're going to pass 0.5 everywhere, so for the mean, standard deviation and so on, 0.5, 0.5, and then here for all the channels 0.5. So yeah, basically this is what we use for mean and standard deviation, and these are now the transformations. Every image is going to go through this transformation pipeline, and in order to work with the images, of course, we need to import them. So we're going to create two data loaders for the training data and for the testing data. So train DL is going to be a data loader, which we get from Torch utils data, and we want to create a data set from the image folder. So we're going to say here data sets.image folder, and we're just going to pass here data/training, and we're going to pass also the transformation pipeline. So that is basically saying take the training directory, treat the subdirectory as classes here, and turn this into a data set. Very simple. Then a couple of things, a batch size, we want to get 32 images at once every time we get a new batch. So that is the size of the batch, as the name says. We want to shuffle the training data for some randomness. We want to load with 4 workers. This just speeds up the loading of the data. And then we also want to say pin memory equals true, which, as far as I understand it, speeds up the transfer between CPU and GPU. I'm not sure exactly what's happening technically. Might have to research that or to Google that. But basically, that is how you do that for the training data loader. Same thing for test data loader. It's going to take the testing directory. Now, we don't need to shuffle the testing data because this is just for evaluation. Sorry, false, of course, not testing. Yeah, so we don't need the randomness. We're just evaluating. It doesn't matter what order we do this in. This is only important for the gradient calculations. And that is now our data. This is how we load our data. Next up, we're going to, transforms is not defined. Yeah, because it's not transforms, it's transforms. There you go. And next up, we're going to define our model. We're going to do it in a very TensorFlow-like way. So we're going to say model is equal to NN sequential. So we're going to use the syntax that is used in TensorFlow, Keras basically. Not going to do it the PyTorch way to have some variety here. And we're going to say the first layer should be a convolutional layer. So we want to have a conv2D layer in the beginning. I'm not going to go into the details of all the different layers we use here, but the basic idea is a convolutional layer has a so-called kernel or filter, and it slides that over the image to extract certain features. That's like the in a nutshell explanation. And the parameters are the following. We first specify how many channels do we get in. In our case, this is going to be RGB. So it's going to be 3 channels, and we want to output 32 channels. So 32 filters essentially. And these filters, these kernels will have a size of 3 by 3. So we're going to pass 3 here. And then we're going to say 1 and 1 for the stride and the padding. And this is now the first layer. We want to follow this up by something that breaks linearity. So we're going to use just a basic ReLU activation function to have an activation function after the raw convolution. And then we want to apply a max pooling layer so that we regularize this a little bit. So we're going to say here nn.maxpool2d2. And now I'm going to copy this and we're going to adjust the values. Now, this one outputs 32 channels, so this one is going to take in 32 channels, and we're going to output this time 64 channels, so we're doubling it. The rest is going to stay the same. Then I'm going to add another one. It's going to take in 64 and output 128. Rest stays the same. Then we want to flatten whatever we get, so nn.flatten layer, and then we want to use a dense layer, a linear layer, for the, you could say, for the reasoning, for the logic. So we're going to say here nn linear, and we're going to do 128 times 16 times 16. This is what we get in here, and we want to output 256 neurons. We're going to use afterwards again a ReLU activation function and a dropout layer for regularization. So dropout with a chance of 0.5, so 50%. And finally, we want to have the linear layer here with 256 in and 4 out, because we have 4 classes. This has to be 4. Everything in between can be adjusted. This has to be 4 in the end, because we want to have an activation, a softmax activation basically, for each of the 4 classes. Now, the important thing is we want to put that model to the device. So we're going to say to device to put this to the GPU if it's available. Then we're going to define an optimizer. I'm going to say opt is equal to optim.atomw, so with weight decay as a separate term. Then model parameters is what we're optimizing, and a learning rate of 1e minus 4. So 0.00004, if I'm not mistaken. All right, so that's the optimizer. Then the loss function we're going to use is obviously the cross entropy loss. So nn cross entropy loss. And now we can get into the training loop. We're going to train this for 25 epochs. I'm going to say for epoch in range 25. Maybe before that, put the model in training mode explicitly if it isn't, although I think this is not necessary. Then we're going to say running loss for this epoch is 0. And what I want to do is want to say for x and y that I get out of the training data loader. So for the batch that we get, I want to 0 gradient the optimizer. So I want to set all the gradients to 0. I want to calculate the loss with the current parameters that we have. So I'm going to make a prediction loss function when the model is applied to x. Don't forget to put x to the device. So comparing whatever the model gives us for x, we want to compare that with y, put that to the device as well, obviously. That is going to be our loss. We're going to add this to the running loss. But before that, we're going to back propagate the loss. So loss.backward. And then we're going to, with all the gradient updates, we're going to take a step in the direction. So opt.step. That is a basic training. And then we're going to say here print. Let's use an f string. Let's say epoch. And then epoch plus 1. Loss was, and then whatever the loss is. Or actually running loss, sorry. All right, so that is the training. Of course, I messed it up. What's the problem? List is not callable. Of course, we cannot just say list. It's, of course, transforms.compose. So we need to use a class here to turn them into one transform. And now we should be able to train the model. We can see the loss is going down. All right, so after 25 epochs, we get a loss of 8.48. And the interesting thing now is, what is the loss on the testing data, on data it has never seen before, and what is the accuracy? So how accurate are we? For this, we're going to evaluate now. We're going to say model.eval to put it into evaluation mode. Then I'm going to say test loss is equal to 0.0. And also in the same line, maybe here, correct is going to be equal to 0. And then we're going to say here with torch.noGradient, so no grad, we're going to say for x, y in test data loader. We're going to do x and y is equal to x2 device, y2 device. And now we're going to see how accurate our model is. We're going to get the logits from our model. So the raw numbers, not softmax or anything, just the logits. It's equal to model applied onto x. Based on that, we're going to calculate the loss. So the test loss is plus equal loss function logits and y. So we're going to compare the output. We're going to get the item and we're going to multiply this with the size of y, so size 0. And then the accuracy is going to be the following. I'm going to say predictions are equal to logits.argmax, so which one has the highest activation in dimension 1. And then we're going to conclude, okay, what is the class that we predict? And we're going to see if that is true. So we're going to say correct plus equals, and then the predictions have to match the actual output, the actual class. We're going to sum up the number of correct predictions, and we're going to get the number as a result here. And then in the end, we're going to say test loss is going to be divided by the length of the test data loader data set. And we're going to say that the accuracy is going to be calculated as 100 times correct classifications over length of the data set. So just the percentage of correct classifications. Now, consider the fact that we have 4 classes, so this is not a binary true or false. It's like you have if you're guessing and you have the same number of instances roughly, you have 1/4, so 25% chance to be correct, which is more difficult than just saying true or false, or yes or no, or cat or dog. So what we're going to say here now is we're going to say test loss is going to be the test loss, and then test accuracy is equal to the accuracy. Let's run this. And we see we get 96%. Actually, maybe I should add a percentage here. I could also use a formatted string, but yeah, I didn't. So 96.49% accuracy and a loss of 0.12. This is very, very good. Now, of course, you want to improve this if you can. You want to train longer. You want to do learning rate scheduling or something. Try to improve these results, but this is already quite a decent result. Now with this code here, which I'm just going to copy paste now, we can also visualize a random image. So what we do here is we import random, we import matplotlib pyplot as plt. We say from torch vision transforms functional to pill image, so to pillow image. We put the model into evaluation mode. We get a random index. We get the image and the label for this random index. We unnormalize the image, so we transform it back. So we multiply and add. And then we show the image, we make a prediction, we show the actual class, and we can just see what our model says for a random image. So it says no tumor, and no tumor is correct. I can run again. It says glioma, and it is a glioma. I run it again. It says glioma, and it is a glioma. It says no tumor, it is no tumor. Now this time here it predicts meningioma, but it's glioma, and so on and so forth. So yeah, that is basically how you can train a neural network, a convolutional neural network in PyTorch to classify different types of brain tumors. Of course, now as an exercise for you, try to make this better. Do hyperparameter tuning, try different architectures, try different optimizers, different learning rate scheduling, model, checkpointing, all that stuff, and see if you can improve the results. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Also, if you want to see more machine learning tutorials on specific datasets, let me know in the comment section down below which kind of datasets you're interested in. And besides that, don't forget to subscribe and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.